the presentation this evening is as the slide says, it's about chokes, balance, and RF transformers, or transmission line transformers. I'm Rick, I'm W5RH. And just the note at the bottom of the screen is there's a PDF version of this presentation already on the Tech Articles website. So if you find it interesting, or more importantly, the reason I put it on there was because there's a lot of references to good articles and books and things down through the presentation. So you don't have to take notes unless you want to, but all the stuff will be online, or is online right now. So when I started doing this about 6 months ago, I said, you know, it'd be really good to have a presentation about chokes and balance and things like that. And so, you know, I started writing down what I knew from just practical experience and so forth. And then I started doing the presentation and researching it, and I got out all my books and all my articles and stuff that I've collected over the years. And I ran into this iceberg thing. You know, what I knew and the practical sense was like 1/6, and then the rest of the theory, design, and the material knowledge for magnetics and all that stuff was just ungodly amount of information. Now, do you need that to do ham radio? No, but if you want to get into it, that's what you're looking at. I mean, there's some great stuff out there, but anyway, that's kind of what I ran into. I am not going to cover any of that design and material knowledge tonight. Let's stay practical. So what are we going to talk about tonight? We're going to talk about passive inductive devices in the antenna system. Now, I'm not going to talk about baluns that are used as the input and output for a balanced mixer in an RF system transceiver. That's not what I'm talking about. I'm talking about antenna systems. We're going to talk about chokes, baluns, and it is baluns. It's not balloons. It's not balums. It's not, remember the David Bowie Bowie thing? Baluns has the same situation. Also, then we'll talk a little bit about transmission line or RF transformers, because they do operate differently. But what I'm not going to talk about are loading coils and traps, which are also passive inductive type devices. However, I'm going to dedicate one slide to loading coils and traps, just to let it know. I've heard it on the repeater, and I've heard people say, they say, well, I've got traps on my antenna, and it makes it longer. And well, there's two different things. There's a loading coil, which is a lumped L value. It's a coil that's used in series with the element, and it increases the electrical length of the element while you can keep the physical length of the element shorter. That's a loading coil. Now, a trap adds a capacitor to that, but the trap, again, is used in series with the element, and it blocks RF at a specific frequency. Perfect example of this is Yagis. You know, you get multi-band Yagis. You got a 10-meter trap, a 15-meter trap, 20-meter trap, or work band traps, whatever. But it is a trap, and it's an inductor and some type of capacitance, some type of the Mosley antennas don't really use a capacitor. They use the housing as the capacitor, things like that. So it's that, hopefully that clears it for some people that get that confused. And rightly so. Antennas are very confusing. I admit that, and I found that over the many years I've been messing with them. They are confusing. Okay, so let's start to talk about chokes. And this is where my main focus is tonight, because chokes are what we use. We can use them on transmit. We can use them on receive. We use them in the antenna system. We use them in our shack and so forth. But it's an inductive-based passive device, and it stops the flow of common mode currents, which are the bad currents in an antenna system or in a signal wire and so forth. And you can see some examples there on the screen. One is a toroid with the coax wrapped around it. The other is beads at the bottom. The beads are put over, they're very lossy, and the beads are put over, and that stops the common mode current from that. The other topic is baluns. Balun is again, a passive bidirectional device, and they can be used in both directions. And it provides typically a smooth transition from coax, an unbalanced line, to a balanced line, like feeding a dipole antenna or the driven element of a Yagi or something like that. But it provides that smooth transition and And it can also be a transformer too, where it is, you know, a 4-to-1 balun or a 9-to-1 balun. Transmission line transformers, it's an inductive device. You can see on the left there in the picture, there's a toroid that's wound with wire. And at RF frequencies, you can't use the magnetic flux type transformers that you use for your 120 volt to 15 volt power supply in your shack. Doesn't work. So transmission line transformers operate with a transmission line. You'll see that on the left there, you have red and green. How about red and blue wires? And there's two of them. Transmission lines have two wires side by side. That spacing has a lot to do with the impedance transformation from primary to secondary. And you'll see on the right there that you've got a schematic of a Guanella type transformer. One thing about a normal transformer or a power transformer is that if you look at the voltage and directions, the primary and the secondary, and like a power transformer, they run in the same direction. The currents run in the same direction and the voltages run in the same direction. On a transmission line, on the primary and the secondaries, they run opposite to each other. That's one big difference. Okay, so let's get into chokes. Why do we use them? Well, we're trying to stop common mode currents that appear on coaxial field lines and interface cables between our computers and our amplifiers and things like that. We're going to stop the common mode currents that are generated at the feed point of, say, a dipole that go when we're going from an unbalanced coax line to a balanced element, so forth. And also, we're going to stop any common mode antenna currents that are generated by just the radiation of the antenna into the shield, the outside of the coax. Okay, so I've mentioned common mode currents, and some of you are probably going, well, what the heck is a common mode current? All right, so inside a coax, let's just take it this way. Inside the coax, you have a center wire. And then surrounding that wire, you have a shield. That's the second part of the transmission line. Well, the voltages and current that are within that coax are differential mode. The voltages are 180 degrees out, and the currents also are the same. So they kind of cancel each other. One's positive, the other one's negative, and so forth. And they travel up and they travel back, and any interface cable, a microphone cable, a control cable, anything like that, the preferred currents are differential mode. So we won't mention differential mode a whole lot in here. What we're concerned about is, for example, on a coaxial cable, the outside of the shield is another conductor. And the reason that is because there's RF skin effect. RF, if you have a battery in your car, the cable going from the battery to the starter motor is very thick, very large. The DC current runs throughout the copper, all of the copper across the diameter of that cable all the way down to the starter motor. Whereas if you start moving up into RF frequencies, the currents will start to flow on the outside. So the middle of that thick copper wire will not be used. It's just the outside. Hence, you can have a shield on coax. And as you get up high enough, inside of the coax is a different surface than the outside of the coax. And so the inside is what you want. That's what you get your power to your antenna and so forth. But a common mode current can be generated by an imbalance at the feed point or radiation or so forth, and it'll flow on the outside of the coax. And it flows right down into your shack and can cause all types of problems. So that's why we're trying to use these chokes, is to eliminate that common mode current. All right. Now, when to use them? Okay, if you have RF in your shack, you know, you transmit on 40 meters and all of a sudden your computer goes, well, JP, K5JPP, he's on here. He wrote an article in the BVARC Beacon in April, and he talked about his dilemma of having RF in the shack and his computers and so forth. And it's an excellent his column is for the newbies in the hobby, but it's just an excellent practical example of how chokes and ferrites and so forth can remove the common mode situations in there. Now that his was more on the transmit side of things. Now on the received noise side of things, that's another issue. We can get received noise generated into the shield of the coax by our air conditioners, our neighbors' plasma TV, although I have a plasma TV and it doesn't give me any problems. But, you know, there's lots of noise around your neighborhood that you can generate noise onto the shield of the coax. Common mode currents can flow down that coax and cause problems in your shack. Now, there's an excellent couple of articles by Chuck Councilman, W5RH, and he's in the Yankee Clipper Contest Club, the ycc.org, and go into the articles. And he especially the one on receive chokes, he talks about he choked every, and I mean every, wire in his shack, his power cables, his interface cables, his antenna wires, everything he choked. And what he found as he did this, he found that his received noise levels just slowly went down, and he had a very high received noise level to begin with. So anyway, chokes can be used for the noise situation, you know, not just quote RFI. So where to use them? You're going to use them on the coax, on the transmission line itself. You're going to use one at the feed point where you get that transition from unbalanced to balance. You're going to use it at the entry of the shack as your coax comes in, and pretty much anywhere in between, depending on your situation. You're going to try to choke all of your power cables, because you'll get noise coming in on the power cables through the you know, your power supplier and your 120 volts. And just choke all your interfacing cables. I mean, you've got a fairly high level of RF in your shack. You know, even if you run 100 watts, they're there. So, and the main thing is, I said I wasn't going to mention differential mode currents anymore, but chokes, they don't diminish the differential mode currents, the good stuff that we want. Inside a coax, any kind of chokes on the outside don't do anything for the inside. So that remains good. It just takes care of the common mode. So one of the things I was talking about is that your antenna itself, the radiation field, and if you go into dipole design, it's okay, hang up your dipole and run your coax straight down to the ground, or straight down as much as you can, and then run it into your shack. Well, that minimizes any kind of radiated pickup from the antenna itself. You know, the field strength of an antenna right at the feed point is quite strong. You can see on this, the red antenna, and the white line is the standing wave current, and it's maximized in the middle, and it generates and can generate common mode currents on that coax. But if you run it straight down, that minimizes it, and then you put a choke right at your shack, and that'll hopefully take care of the problem. Now, the worst case scenario of that is if you hang a dipole and then you take your feed line and just run it almost in parallel with the antenna, you are definitely going to generate common mode currents onto there. Now, maybe that's all you can do. Maybe that's your situation. Your homeowners, you know, you can't put up a high antenna. You got to put it low. You got to run the coaxial cable at an angle and so forth. The thing to do is you put multiple chokes in line, as many as possible. Put one at the feed point, put one midway, put one right outside the shack. Use more than 2 or 3. Keep using them along that line, the coax, and until you take care of that problem. So what type do you use? Well, it depends on what you're trying to do. The one on the left there is the typical, oh, you just wind, you know, 8 or 9 turns, about number 10 can, and put it on there and so forth. Yes, that works okay. But if you read the articles and stuff, They work fine, but they're not real broadband. If you're trying to work multiple bands, excuse me, hang on, fell out of my ear. If you're trying to work multiple bands, maybe those don't work so good. Maybe their impedance to that common mode isn't as great as some of these others, like the beads that you see in the middle at the top. And the beads can be, you can slip the coax through, or you can use the ones down below where you get the snap-on beads. And then another way to generate a choke is using a toroid, some type of magnetic device, either iron powder or ferrite, depending on the frequency and so forth. And then you can use that. And you can make little jumpers like this and just put them in line in your coax anywhere you have a connection. So unfortunately, as much of the world of RF is applying chokes to a problem is kind of hit and miss. You can't see RF. You could, and in this situation, you really can't measure much of this. It's, like JP said, well, it killed my computer, so I put chokes on these things, and that seemed to help a little bit, but I had to do some more. And it's kind of hit and miss, but knowing a lot of the detailed information about common mode and how that works, there's a lot of books out there that explain that. Get schooled up on some of these and read specific stories and anecdotal notes about situations of people having something the same as you. There's some really good information out there about using chokes. Palomar Engineers, their website, I've got a picture of their one website coming up. There's an article that was excellent. Mark Janzer turned me on to it. It is probably the quintessential note about using chokes, and it was in Radcom in May 2015, and it's called High Performance CM Chokes. You can Google this, and it will come up. It's it's going to be on the BVARC Tech Articles webpage. It's not yet. I wanted to put it on, but it's 14 megabytes, and I've got some software on this computer here that I can lower that number down into the 2 and 3 megabytes. But it's 8 pages of just excellent use, measurement, design, doing all stuff about high performance common mode chokes. And I did mention Chuck Councilman, his 2 articles about common mode chokes, and then on the excellent receive and cheat mode chokes. Those are 4 really, really good articles about common mode chokes. Now here's the Palomar website. Of course, they sell all types of stuff. They sell the kits and the filters and feedline chokes and transformers and baluns and all that stuff. But they do have, the bottom is they have tutorials about how to kill things and what to look for and what specific mix of ferrite material do you use for certain frequency ranges, things like that. That's all on the website, so to get you up to speed real quick. Okay, this is the article by Steve Hunt, the high performance common mode chokes, that was in Radcom. I'll get that on the website, and I will put that. I'll put a notice out on the reflector that it is up on the website, so you can have it. Even if you don't have problems, you need to have this in your library for sure. This is one heck of an article. So let's talk about the next thing, baluns. Why we use them? Okay, well, baluns are used at the transition point between coax and a balanced antenna, driven element, things like that. And sometimes that transition can cause problems with common mode currents on the feed line, as we talked. The other way to use a balun is if you want to run an end balance tuner and feed a balanced antenna system. That's a lot of antenna tuners, the manual tuners, have a balun, typically a voltage balun at their output, so you can run into 300 ohm or hopefully not 300 ohm, it's TV, but 450 ohm or 600 ohm ladder line. So when are you going to use that? Any time you really have a transmission line transition from coax to open wire, or anytime you're feeding a balanced antenna with coax. And on a Yagi, if you put a balun right there at the feed point, you're going to maximize its performance. So the standing wave currents on the driven element are going to be balanced and equal on either side, so the Yagi can perform to its desired, situation. So where to use them? You're going to use them at the feed point. And like I said, you're on a Yagi, you're going to maximize the performance. You're going to keep the standing wave currents balanced and so forth. So it's mostly baluns are used at the feed point of antennas. Now here's the example that you have a coax to a balanced antenna. You have a source at the very bottom, and it runs to the center wire of a piece of coax. You'll see that coaxial feed line runs up through the center, and that's one current. The other current that you want, the differential mode current, is another one, and it comes down the inside of the shield. These are reversed. It's one is going down and two shows up. So the inside of the shield and the wire are the differential mode currents. Those are the ones you want. However, at the top, when you separate the coax to the both sides of the dipole, part of the current goes to the dipole or the element itself, and there's another part of the current that goes along the outside of the shield, like we talked about. You have the skin effect and the two surfaces, or the outside of the inside and the outside of the shield. Part of that goes down the outside of the shield, and it actually divides the current. So the current on one side of the antenna is much greater than the current on the side that you have a split. So that's an issue with especially Yagis when you're trying to get everything out just equal and so forth. And this is an EasyNet model of an example of that situation. You'll see on the black horizontal wire is the antenna. The vertical wire, number 3, is the coax, the shield. It's another, quote, wire. And it shows you the problem with, look at the differential between the standing wave currents of 1 and 2. And then you also have the vertical on 3, So that's not something you would like in certain situations, as, again, a Yagi. Now, if you throw a balun in there, what's going to happen is it's going to balance things out, and you're going to get a nice antenna in the green, and then you're going to get the purple. That's going to be the standing wave current. You can see it's balanced and so forth. So you've got no common mode coming down the coax. All your power gets radiated out into the antenna, and you get maximum radiation and maximum performance, no matter whether it's a dipole or a Yagi or what. But that's it. The balun does help with that situation. So what type to use? It depends what you're doing. Are you doing wire? Are you doing Yagis and so forth? You'll see up in the left corner is that DX Engineering is a 1-to-1 balun, high power. Coax comes in, and the output for the wire element goes to the connections on top with the wing nuts there. Another one is the bottom is the jet stream. That's typically, I think that's a 4-to-1, it says. So the balun can do some type of impedance transformation. The picture in the middle there just shows what's inside. It's a toroid with transmission line, 2 wires wrapped around that toroid in a specific series and parallel configuration in order to get the choking of the common mode, and 2, the impedance transformation, if that's what you're trying to do. Down below that, 1JR, that's Joe Reesert, his balun that came up, it's just coax, and then you're choking the common mode currents, and what comes out the other end is a balanced feed. It's a 1-to-1. You can also, you don't have to use ferrites all the time. If you have frequency specific things, like the one on the right, it's a 4-to-1 balun. It uses a half wavelength of 75 ohm coax or a 50 ohm coax, depending on your system. But it gives you a 4-to-1 transformation. I use one of these on a 2 meter 5/8 wavelength J-pole that I built many years ago. I couldn't get a match, just couldn't get a match anywhere. And I built this balun, and it helped tremendously, and it worked just fine. It did it exactly as it says right there. So using a bit of coax to generate a balun. However, it is pretty frequency specific. The other baluns, as you see, are broadband. They typically will go, 160 or 80 through 10 meters. Okay, let's go. So a few characteristics about baluns. Most are bidirectional. They provide the unbalanced to balanced transition. You can transform the ratios, impedance ratios, 1:1, 1:2, 1:4, 1:9, so forth. Whatever you want, you can generate, and generate any kind of transformation that you need. They use the toroids, the magnetic material, to increase their choking property and increase the inductance of just having a coil. And like I said on the coaxial balun that I had in the other page, it is pretty much a single frequency. One thing about baluns is that as they're typically, for example, 1:4, so 1 being 50 ohms, 4 would be 200 ohms, but that's the R value in an antenna feed. So as you move away from that sweet spot frequency, your feed impedance becomes more reactive, and so the ratio of the transformer, that 1:4, does suffer a little bit, and sometimes can, if you go too far, like on 80 meters, you may be able to get it so far out that it doesn't perform very well at all. But a lot of these baluns that you'll find that you purchase are broadband, and they will cover at least the ham bands and so forth throughout 80 and 10 meters. So let's talk a little bit about RF transformers. That's the third subject. They're also called transmission line transformers. They don't use, as I said before, they don't use a mutual coupling as a standard power transformer, where you have a core and then you have a primary and a secondary, and you have 120 volts in and 15 volts out. That's not the way these work. They utilize ferrite non-powder toroids and beads and so forth in order to enhance their operation. So they're used typically to match feed lines to antennas. I mean, or feed lines to feed lines. If you have a 50 ohm output of a transceiver and you want to run 300 feet of 450 ohm ladder lines so it's lossless, you just put in a transformer to do that, and you can wind typically anything you need: 1:2, 1:4, 1:9, 1 to 1.5. There are books out there written by Jerry Civic, who we'll get to, that outlines all this stuff. Now, the thing of it is that the RF transformers typically use 2-wire transmission lines, and you'll see that's why a lot of the toroids, you'll see they're bifilar wound. Some of the windings are side by side. Others, at the smaller gauge wires, 20, 24, 26, 28 gauge, they're typically twisted, and that distance between the wires, just like on open wire line or 450 ohm, that distance defines the characteristic impedance of the feed line. The distance between the wires also defines the characteristic impedance of that 2-wire transmission line that's used. And they can provide, as I said, broadband matching, 80 to 10 meters, and they work fairly well. And the calculations for, in primary to secondary voltages and impedances and so forth work the same as they do on a normal transformer. There are some things you have to concern yourself with. As I said, the 2-wire transmission line, depending on the thickness of the wire and how you're going to wind them and so forth, that gets thrown into the mix. So The most popular configuration for an RF transformer is the toroid. You have Ruthroff configurations or Guanella configurations. These are the guys that came up in 1939 and 1940 something or 50 something. They came up with these configurations. Shown below is a Guanella. It's a 1-to-4, and you can see that each of the windings, and like I said before, on an RF transformer, transmission line transformer, excuse me, the currents traveling within the windings are opposite, unlike a standard power transformer. Anyway, so Guanella came up and he puts his inputs are in parallel and then the output is in series. It's one of the ways to get a 1-to-4, and they're wound in a certain way and so forth. Here's some other schematics of a Guanella there, and then also at the bottom here, this is a way to get an RF transformer. Of course, it can be used as a balun. You know, you have 50 ohm coax coming in, and you just have parallel lines with beads, and then the output is a balanced output at the other end, because you're not generating any common mode current. You're controlling the currents that are inside and forcing them to be balanced on the output. So, okay, so many different ratios on RF transformers can be wound. You know, you pick one, pick what you need, and you can wind something, and you can wind it as a balun, balanced to unbalanced, or unbalanced to balanced, or unbalanced to unbalanced. And it all depends on the configuration and so forth of how you wind it and what you need. You know, I mean, a dipole's a balanced antenna, but a vertical isn't. Vertical plays itself against ground, and so it's unbalanced. So they're very, very flexible, and again, this is really high level stuff, and I would encourage you, if you do need something special, to use some of the references I'm going to show you here in a minute. Like Jerry Sevic's book, this is pretty popular book concerning baluns and so forth. Now, this is an older version. There is a newer version that you can get that Jerry Sevic wrote. I mean, it's all, anything you need is in that book. How they work, why they work, what to use, ferrite material, things like that. That's all in there. So there's a bit of crosstalk here. If you've noticed that I talked about chokes being baluns and baluns being chokes and things like that. But, you know, a choke is a choke and an RF transformer is a transformer, but a balun can be the combination of a choke and a transformer. It can be both at the same time. And a choke can be a balun. For example, you have a feed point on a dipole. If you put a choke at the feed point, that choke is going to inhibit those common mode currents that are generated, as I showed in that one illustration. They're not going to allow those to occur. So you're going to get a, quote, balun effect just by using a choke. So what you call each of these things is really dependent on how it's used. You say, well, I have a balun at the feed point. Well, I have a choke at the feed point. Well, you can call it a choke or current balun, line isolator, matching network, transformer, whatever. It all depends how you use it is what you call it. So let me show you some practical examples. I mean, that's why we're here, is, you know, so B&W has this antenna. Gus, you're familiar with this antenna, so are you, Dave. The TFD, the terminated folded dipole, or the original configuration was that it was tilted to be omnidirectional. T2FD, TTFD. But you see that the feed comes to a 4-to-1 balun, and that's a perfect example of needing that transition from 75 ohms to 300 ohms being a 4-to-1, because that's what is needed in order for that antenna to work properly with the terminating resistor of 390 ohm and so forth. There's other configurations on this antenna that use different balun and transformer ratios and different terminating resistors. But this is the more popular, I guess, or more historical type. Another example is the Carolina Windom, which really isn't a Windom, but that's okay. It uses a 4-to-1 transformer, just a transformer at the feed point, and that's fine. But then they put a current balun 22 feet down the RG8X, and they call it a line isolator. They really aren't running any kind of choke at the feed point. They want that vertical portion to radiate. They want that common mode. So if you think back to that easy neck model that I showed where it was unbalanced, the vertical coax, the common mode on the coax had pretty substantial current on it, and that causes radiation. So they get horizontal radiation out of this plus vertical radiation, and they do that by using a line isolator. W5RH, Dan, he has one of these at his house that I helped him put up. So okay, one of the more popular antennas in the last couple of years is the end-fed half wave, and what they use is a 49-to-1 transformer, and this is just a perfect example of an antenna that uses an RF transformer and a practical implementation of that. There's lots of information on the web about building not only the transformers but the antennas themselves and why they work. I mean, they got one piece of wire fed with this transformer and it works all bands. It's really amazing. There's a fellow, I think he's in West Virginia, that has a great website about this. Something to look at if you're looking for a multi-band antenna with one. So throughout all of this, you're going to have to buy something, either buy parts to build something or buy something that's already put together. For ferrite material, for toroids and beads and things like that, Amazon is probably the more famous, but Palomar Engineers has been around for a long time, as I showed you that page on their website with all types of information. A new one that I've found is quite interesting. They've got some great information. Is KF7P Metalworks. They have ferrites and chokes, and they have a great tutorial page and all that stuff. It's great to have a read of that stuff. They also make all types of stuff for towers and grounding and running coax and switches and lightning arresting and all that stuff. It's great stuff. Of course, DX Engineering, they have, off-the-shelf baluns and antenna system parts. So if you're looking for baluns and chokes and things like that, you can Google, get on to Amazon or whatever, but stick with the ham radio manufacturers because they will provide you with a bit of information. So sources for a lot of this information, and again, lack of information that I haven't told you that still exists out there. I mean, JP's article, you got Chuck Councilman, he's got those two articles. The Steve Hunt high performance chokes article is excellent, and Steve Nichols is another G ham who did a PDF, or he did a PowerPoint show, but he also put it as a PDF, and you can get it at that link right there. And it's really good. It's very good. It's using Baluns Ununs. It's a very practical, in fact, it's even better than my presentation as far as telling you how to use it and where to use it and so forth. If you really want to get into things, go see K9YC. That's Jim Brown. He's an audio guy, but he's also a ham. And he's got tutorials and stuff on all types of solutions for audio and ham and so forth. And Roy Llewellyn, W7EL, now he's the guy that gives us Easy Neck, Easy NEC. I call it Easy Neck. He's the one that writes the interface for the NEC engine. And he wrote an article and Baluns, what they do and how they do it. And this outlines the imbalance current that flows in the outside of the coax. He takes that situation and tells you why that occurs and how it occurs and how to fix it and why balance work and so forth. And you can get it at his EasyNet website. It's also in the Antenna Compendium, ARL Antenna Compendium #1. But Roy's a real sharp cookie, and a really, really good article about basics of how balance work. So one book that is available online now, there is Jerry Civic also wrote a transmission line transformer handbook, but what he did here, and I just found this a couple of weeks ago, this is available online, but it's something that he wrote for Amazon, and it's very specific to certain designs, but his explanations of how these things work and so forth in the beginning are just absolutely excellent, and it's available online as a PDF. So I would encourage you. This is one book, another book that you got to have in your library, and just your electronic library PDFs. As I showed you the other Civic book, I showed this before. This is about Baluns Ununs and so forth. That's a pretty good book. That's one that everybody refers to. And then the Palomar Engineers is a good source. I've showed you that before. That's a great website for information. If you really want to get to that below the water surface information about designing and building and applying chokes and balance and RF transformers and so forth, Doug DeMaw, W1FB, is now a silent key. He wrote tons of stuff years and years ago, but he came up with this book, Ferromagnetic Core Design and Application Handbook. And if I had to be honest with you, I probably understood 6 or 7 pages out of the 100 or so pages that were in there. I even kind of gave up reading it. But it's if you want to get, again, below the water level, this is one book that you got to have. MFJ sells it, and you can buy it online and so forth. If you're having trouble, like JP had in his shack and so forth, the RFI handbook is a good one from ARL. It outlines all types of solutions and so forth. And this is the 3rd edition. This is the latest one. It's really good for helping you solve problems. Okay, so I'm doing all this research, and I'm looking online, and I'm reading all this information, and I go and I type in, I don't know, I typed in 4-to-1 balance or something like that, and look what comes up. It's a Walmart. Walmart is selling 4-to-1 balance. Of course, sell anything to make money. But I just thought that was kind of extremely funny and sort of ironic, Walmart selling 4-to-1 balance. I mean, how many people that go to Walmart would understand what this is? But anyway, I thought that was pretty funny. So that's all I have for this evening. That's all I got to say. If you have any questions, you can email me. I'm in the roster. If you need more information about any of these sources or anything, I have all these sources. I have tons more books and things like that. But, I'd be happy to entertain any questions. I don't claim to be an expert on any of this stuff. I just find it all extremely interesting and fun to dig into. So,
hey, Rick,